One of the best uses of logarithms and exponents in the real world is graphing actual data on a log scale. Let me kind of illustrate what the problem is with this with a very crude graph example, looking at different graph scales. So if I were to try and draw a graph of the US stock market over the past 100 years, now this is obviously not going to be perfect, but the general idea is it's going to wiggle a bit and it doesn't look like much is changing, and then all of a sudden it takes off at the end. The problem with this is it's hard to tell the difference between minor changes in one spot and major changes in another spot and how significant they actually are, because these numbers are so different from each other. The reason is we've just got a regular XY scale here, and it's really hard to see. And so what we have found is easier is if we've got an exponential growth situation, like this graph, we can change the Y scale to what's called the log of Y. And we can use any base. I'm going to use base 10 for this example. We'll use a base E for another example. So make sure you look at the Y scale to decide what the base is. But what's neat about this is it will convert the graph from an exponential equation to a linear equation. So then it becomes easier to see how big changes are and how the graph is moving around. It appears linear when we do this type of graph. And the name, when we do this log Y scale on the y-axis, we call it a semi-log graph. They also have log-log graphs where we do the log on both the x and y scales. We're not going to look at that here. We're just going to do semi-log graphs. So we're just going to make the y scale some type of logarithm. So what that does then is it allows us to do things like graph f of x equals 3 times 2 to the x on a semi-log scale. Now, technically, we could pick any base we wanted to. What we're going to do for this example is we're going to use base 10. So one way we could graph this is we could take our x coordinates and calculate f of x's value. For example, if x is -3, I could plug -3 into that exponent and do that on my calculator. 3 times 2 to the -3. My calculator tells me the answer is 3/8. Then I could plug in maybe -1. 3 times 2 to the -1, my calculator tells me that's 3/2. I could plug in 0. 3 times 2 to the 0 is 3. I could plug in 2. 3 times 2 to the 2nd power is 12. I could plug in 5. 3 times 2 to the 5th power is 96. The problem with graphing these points on a regular scale, like we've seen before, is the 3/8 and 3/2, the difference in there looks so small, and then all of a sudden it gets huge to 96, and I can't make a scale that goes up to 96. So what we do is we'll make another column for the log of these answers, and that's going to scale it down to a log scale, a semi-log scale, where it'll be easier to see the linear relationship here. So what I'll do is simply take the log of each of these numbers on my calculator, and I'm just going to do log base 10. And as I do that working down, the log of 3/8 comes out to be -0.43. The log of 3/2 is 0.18. The log of 3 is 0.48. The log of 12 is 1.08. And the log of 96 is 1.98. Now, instead of having something that's very difficult to graph, I actually have something that's quite easy to graph. I'm going to make a bigger scale on the y just because it doesn't go much bigger than 2. And so now as I graph these points, when x is -3, I'm going to graph on the log value of -0.43. When x is -1, I've got a y value of 0.18. When x is 0, I've got a log value of 0.48. When x is 2, my log value is 1.08. And when x is 5, my log value is 1.98. And just as expected, all these dots form a straight line on a semi-log scale. And I should label the y-axis as the log of y, so I know it's a base 10 because there's no base written. So this will start to beg the question, what is the equation of that line that we drew? Well, we can convert an exponential to a semi-log line by taking the log of both sides and use our log properties. Let's take a look at doing that on this example that we were just working with. The example we were working with was f of x equals 3 times 2 to the x. And if I rewrite this as just y equals 3 times 2 to the x, that would be on a normal y scale. Well, we want the log of y, so we'll take the log of both sides. And that's going to give me the log of y is equal to the log of 3 times 2 to the x. Now we know whenever we have a product inside a logarithm, we can expand it to be two separate logs. And so now I have the log of y equals the log of 3 plus the log of 2 to the x power. But I also know that an exponent inside of a log can come out in front of the log. So now I have the log of y equals the log of 3 plus x times the log of 2. Well, these values I can actually put in my calculator and figure out what they are. So if I've got the log of y is equal to, when I put in the log of 3 on my calculator, I get 0.4771 plus x times the log of 2, which is 0.301. And now normally we like to write our equations as y equals mx plus b. So we'll do the same thing here. We'll do log of y is equal to, the part with the x first, 0.301x, plus my y-intercept of 0.4771. And so now this is the equation of the line that we graphed on the semi-log scale. We can also go the other way. I could take a graph of a line on a semi-log scale and convert it back to its exponential form. For example, let's look at converting a semi-log line to an exponential equation. The way we're going to do that is we'll get the equation of the line and then convert it back to an exponential equation. Here's what I mean by that. Let's start with a point at 0, 2, and we'll put our next point at 3, 1. And if I were to connect those dots, we end up with this line. We're going to label the y-axis as the natural log of y. It's important to note this is a natural log of y on the y-axis. That means I'm using a natural log this time, not a base 10. It's always important to check, are we doing natural log or base 10? When trying to pull information off this graph then, we know from lines that I need to know the y-intercept here, which is 2, and I need to know the slope of the graph, which I can see goes down 1 and over 3, so my slope is -1/3. Plugging that into y equals mx plus b then, I've got y equals m, which is -1/3 x, plus b, which is my 2. But that's not actually what y equals, that's what the natural log of y equals, because that's my scale. We can then convert this equation to an exponent by using the base, which we know with natural log is a base e, raised to the exponent of -1/3 x plus 2, all that's going to equal y. Then we're going to use some of our exponent properties to split this up. We know when we see a plus, that means we've got two bases. And I'm going to switch the order. I'm going to put the whole number first and then the -1/3 x second. And then I'm going to go one step further and I'm going to put the e to the -1/3 in parentheses with the x outside of the parentheses. That's going to put it in the exponential form that I want because I can do e squared on my calculator. E squared is going to be 7.3891 times, I can do e to the -1/3 on my calculator, again being careful with parentheses, gives me 0.7165 to the x equals y. And now I have converted that semi-log line into an exponential equation. So that's kind of the process we go through to convert that log scale either to an exponential equation or an exponential equation to a log scale. However, where this really comes up is in what's called exponential regression. For example, if I'm interested in the value in billions of dollars of the U.S. imports from China. So in a given year, let's go 2000, 2001, 2002, 2003, 2004, and 2005. And the value of that import in billions of dollars was 100 billion, 102 billion, 300 million, 125.2 billion, 152.4, 196.7, and 243.5. To make this easier to graph, I'm going to introduce a new column that's going to be time. I'm going to let time start at 0 in the year 2000, and then 1 year later, 2 years later, 3 years later, 4 years later, and 5 years later. So if we wanted to come up with a line of best fit here, what we would find is because of how fast it's growing, especially at the end, it's taking off at the end and it's going to really skew my scale. And so instead we're going to do an exponential regression and find the exponential line that best goes through each of these points. And we can do it in much the same way that we did before. We can take the log of all of our answers, plot all those points on our graph, convert it to a linear equation, and then convert it to an exponential equation. But that's a lot of steps. So what we're going to do is we're going to rely on our old friend Excel to help us out with our exponential regression. So what I've done first is I've copied the information from our data onto Excel. And what we're going to do is we're going to make a graph of time compared to billions of dollars. First as a scatter plot. To do that, I'm going to go to Insert. And under Charts, click the scatter plot with all the dots. Let's make this a little bigger so it's easier to see. And there's my points. And you can see it's kind of got that exponential curve shape to it. I can actually draw the best fit exponential curve shape by going to Chart Elements, down to Trend Line. There's a little arrow where I can select different types of trend lines. Notice the linear goes kind of straight, but it doesn't bend. The exponential really bends with the dots. And so that exponential trend line is probably the best fit for this model. To figure out the equation of that trend line, I'm just going to double click that trend line. And it's going to bring up my Format Trend Line options. And if I select the bars, down at the bottom, I can display the equation on the chart. Very similar to what we did with linear. In fact, we can switch between linear and exponential on here as well, and other types of regression that exist. We want exponential. I'm going to click Display Equation on Chart, and it's going to give me this equation. 90.535. Let's make that a little bigger, actually. If I click in it, I could double click in it and go to the font size here that comes up. And I can make it a little bigger so it's easier to see. 90.535 e to the 0.1888x. So Excel's linear regression told us the equation was y equals 90.535 e to the 0.1888x. We're going to convert this, though, to a regular exponential in the form y equals a b to the x. I don't want to have that e in there. And the way we can do that is we can look at that e to the stuff and actually put that part in the calculator. So we'll have y equals 90.535. And then on my calculator, I can actually type in e to the 0.1888, and it's going to give me a new base of 1.2078. And that's all raised to the x power. This then is the exponential regression equation that best fits the data from China's imports. It's your turn to practice with some of these. Take a look at the assignment. Bring questions to your instructor. It's been a pleasure working with you over these past few weeks in these videos. Thank you.